Here in 3.3 we're going to take and look at solving systems of linear inequalities. There's just one objective to solve systems of inequalities by graphing. Now there's definitely a lot of review here, and I think if we can get the review down and remember what we've done sort of in the past, it makes this lesson go by pretty quickly actually. And so the first thing I want to do is remember the situation we had for some of the inequalities that we did back in Unit 2, where you were a blind farmer, that you own land in between Fort Scott and Pittsburgh. And if you remember, what we're trying to do is create a boundary between Fort Scott and Pittsburgh so that we can establish which side is the good side and then obviously which side is the trashy side. And so that's what we're going to be doing here with systems of inequalities. Just we're going to be doing it multiple times rather than just with one inequality. We'll be dealing with two or possibly three with some of the absolute value ones. So we want to remember the inequalities, and I'll go over that a little bit more, the process of that, but I think if you can remember the situation of being a blind farmer, creating the boundary, determine if it's dashed or solid, test a point, which point do we like to test, 0, 0, and then we can shade the true region, I think you're going to have a great opportunity to be successful on this lesson. Let's take a look at one of these. This is again just a review of graphing inequality. So what I want to do is momentarily just convert this to an equation. Now, what's key here is I put this on purpose because I wanted to make sure we saw that this is negative 1/4 as our slope. This is another way we could write that exact same thing. So note that, because that's something that you might encounter once in a while, is equations or inequalities written like this, which simply means the x on top means it's on the side. Now it's in slope-intercept form. I momentarily convert it to an equation so I can plot some points. Notice my y-intercept is 1. And then my slope is a negative 1/4, and so I can go down 1. And I want to make sure I go the right direction. I would go this way 4, or maybe up 1, and then this way 4 as well. And but what we notice here is we're going to end up creating this line that we go ahead and graph. Now, once we decide, okay, there's our boundary, we got to determine if it's dashed or solid. If you remember, the inequality sign is going to determine that, and so in this case, it's going to be solid. Remember, if it has a line, it is a line. If it doesn't have a line, then it would be dashed. So in this example, we would have a solid line. Then what we got to do is remember, anytime we're graphing inequalities, we should be thinking of shading. Okay? And some of us did that well on the Unit 2 test. Some of us maybe struggled a little bit. So we've got to remember, anytime you deal with inequalities that you're graphing, shading should be involved. So let's make sure to test a point here. And we test 0, 0. And we plug that 0, 0 point back into the inequality right up here. And so what we notice, what we get is we get 0 is greater than 0 plus 1. 0 is greater than or equal to 1. Hopefully you notice that that is a false statement. So what we've done is we've tested the soil. That is the false or foul side. And we want the true side, which is over here. So what we want to make sure to do is always shade the true region. And what that represents is all of our solutions are found on the boundary or above the boundary for this example. Okay? And so that is what we're going to be doing, but multiple times. So that really leads us into systems, which is what we've been doing in Unit 3. And if you take a look here, here's a system of equations. We have multiple unknowns with multiple equations. We're going to be graphing them at the same time. And so I want to go ahead and label these. This is 1, this is 2. And I'm going to graph number 1. So you can either use a t-chart or slope-intercept form. For this one, I'm going to use x and y-intercepts because I'm going to use the slope-intercept form for number 2. So I'm going to plug in 0 for x. And notice what we have is negative 3y equals 5. Negative 3y equals 5. And so I divide by negative 3. And so what you notice here is we get negative 5/3. If I plug in 0 for y, what I get is I get 2x equals 5 divided by 2, and what we get is 5/2. So yes, there are fractions here, but this is simply 2.5, 5/2. So I go 2.5 over, put a dot. This one right here, which is our y-intercept, is negative 1 2/3, which is almost negative 2. And so I can almost go down to negative 2, and we get something that looks like this, and then we can go ahead and connect the dots. So it'll look something like that if I was graphing it. If I was doing number 2, I'm going to go ahead and use slope-intercept form for number 2 because it's in slope-intercept form. So my y-intercept is 0, my slope is 2. I go to 1, that's my y-intercept, and a positive 2 slope. So down 2 over 1, down 2 over 1, and so on. And what you'll notice is, and my red line's just a little off, I think they probably cross right around in there. Okay, and what we've done in the past is we said, oh, where they intersect is the solution. So we graphically look to where they intersect and figure out what is that value. You notice it crosses here, and I won't give you one that crosses like that. So most likely they either cross here or right in here. And to check, it would either be negative 2, negative 3, or probably negative 3, negative 4. So let's try negative 2, negative 3 real quick. If I plug in negative 2, I get negative 4 plus 1, which is negative 3, so that works there. If I plug in negative 2, I get negative 4 plus 9, which is obviously 5, and so that works in that one. So my first instinct was right. Negative 2, negative 3 was our solution. My red line just dipped down a little bit. Okay, so that's what we just finished up doing in 3.1 is graphing those inequalities. But now what we want to do is go ahead and proceed with how to graph linear inequalities. In doing this, what we want to do is, and this is going to look very familiar to you, we're going to convert the first inequality to an equation. We're going to create the boundary, t-chart, plot points from the slope-intercept form. Determine if the boundary is dashed or solid. Remember what does that is our inequality signs. Then we're going to test a point. Usually you pick 0, 0 unless it's on the boundary. Then we're going to shade what we call the true region. And then we're going to repeat that process for the second inequality, but graphing it on the exact same plane. And so we're going to have two boundaries that are shaded. And what we're looking for is not where the lines intersect, but where the shaded regions intersect. And so I'm going to use two different colors for these inequalities. So we're going to use, let's go ahead and use red and blue. And obviously red and blue make purple, or yellow and green, or yellow and blue make green. We could use that as well. But we're going to label these again. And number one, I'm going to momentarily convert to an equation and go ahead and graph the boundary here. So this is slope-intercept form. So my y-intercept is a positive 4. So I go on my y-intercept. And then my slope is a negative 2. And so I want to make sure it goes negative, so down 2 over 1. Now remember, it's negative 2 over 1. We don't have the fraction there, but that's what it means. And then you can plot some more points if you need to. Now we've got to determine if it's dashed or solid. And if you notice, this one is dashed. And that's going to be something you want to really keep an eye on. And we talked about it when we did inequalities. But we've got to be very careful not to put a solid line when we need actually dashed. And what we want to do is we want to test a point, so 0, 0. So I go back up here and I plug in 0 for y and I plug in 0 for x. And I want to figure out if this is true or not. So I get 0 is greater than 4. And I say, well, no, it isn't. That's false. And so this is the false side. That obviously means this is the true side. So I'm going to go ahead and shade the true region. Let's go red in this case. Okay, so there we go. And that's usually where we end up with just a single inequality. But now what we're doing is we're going to go ahead and do a second inequality on top of that one. And so my second one is also in slope-intercept form. You can rearrange them if they're not. We'll look at one of those in just a moment. So my y-intercept is negative 2, and my slope is actually technically 1. And so I go to negative 2, I put a dot, and my slope is 1. So and you can see, there we go. This looks pretty good. Down 1 over 1. I get a few more here, so my line looks really nice. And I go ahead and connect these dots. This one's going to be solid. And if you look right here, this is telling me that it's a solid boundary. So I can connect those dots with just a solid line. At that point, we do want to test a point. Hey, let's go 0, 0 again. So I go and I plug this time into this inequality. So 0 is less than or equal to 0 minus 2. Is 0 less than or equal to negative 2? I believe that's false as well. 0 is actually bigger than that. So this is false. This side of the blue one is true. So you've got to sort of ignore the red. And you've got to sort of see this whole bottom part of the blue be in the true region. And we always want to shade the true region. And so everything below this blue line would end up being our solutions for the blue one. Now, what's the solution to the entire inequality, though? What we're looking for is where the shaded regions overlap, if there is one. And so you can sort of see a little bit of purple right there. I know we sort of want to stay away from purple. It's not Pittsburgh purple, though. Let's say it's K-State purple. But what we're looking for is the overlap of those two. And what you'll notice is it overlaps there in this triangular region. That goes on and on forever. But that would be all of our solutions. And so sometimes you'll see me or the book will just sort of erase all this other stuff. You don't have to. But what you need to do is you need to make sure to identify where the solutions are, which in this case is this right region. So any point that falls in this region, I mean, we put a dot right there. Or maybe even on the x-axis, like that's 4, 0. 4, 0, if we bring them all the way over here, will work in both of those inequalities. And that's the key, is the shaded region here where they overlap is a solution to that system. It satisfies both inequalities. Let's take a look at a couple more here. Take a look at the first one. Notice that it's not in slope-intercept form. So many of you like slope-intercept form. So let's go ahead. I'm going to label these. So number one, I'm going to put in slope-intercept. So I'm going to first go ahead and subtract 3x. I need to convert it to an equation. Almost forgot to do that here. There we go. And then I can divide everything by 2. As long as I do it to both sides, I should be in business. And so there's my slope, negative 3 halves. and then I got a y-intercept of 3. So I go to 3, I got a negative 3 over 2 slope, 1, 2, 3, 1, 2, there we go, 1, 2, 3, 1, 2, and I can keep going, but I got enough there of my boundary. I determined that it is solid in this one. It's going to be solid for the second one as well. Let's make this one, let's go yellow and blue, and so this one's going to be yellow, and so there you go, there's a solid one. We do want to test a point, let's go 0, 0 again. We plug that into this one, and I get 0 plus 0 is greater than 6. Is 0 greater than or equal to 6? I don't think so. That's false. So this side must be the true side. So I'll go ahead and keep it just like this yellow, not like that. Okay. Then what we want to do is let's go ahead and make the second one in blue, number 2. And I go ahead and I put this in slope-intercept. Well, watch your negative here. It's still there once I move the 4x. Okay, so be careful not to drop it. Now I change the signs of everything. It's just like multiplying by a negative 1 is what we're doing here. And so I got negative 2 and I got a positive 4 slope. 1, 2, 3, 4 over 1. 1, 2, 3, 4 over 1 and so on. This one's also 1, 2, 3, 4 over 1. This one's also solid if you take a look there at the inequality sign. And so this tells me it's solid. And so I go ahead. Now 0, 0 is not on the boundary. It's really close, but it's not. It's actually on the left side there. So I'm going to go ahead and plug in 0, 0 back into the original, keep in mind, and I get this statement here, 0 is greater than or equal to 2. We keep getting a lot of false statements. But this is the false side. This must be the true side. So again, I ignore the yellow for right now. Now what we're looking for is where yellow and blue make, obviously, green. And so where we're going to shade, or what our solutions are going to be, is the green region. Okay? Which is, in this case, similar to the last one, so it's all the way over here to the right. But that ends up being all of our solutions right there. You can leave the blue and the yellow if you want, as long as you shade in darker the area that's our solutions. For some of you don't like that, that's okay. You can get rid of that, and that would be fine as well. I will take either one, but our solutions are over here, bounded by those two boundaries there. Okay, let's take a look at the one here at the bottom and sort of see what's going on here. And so I'm going to go ahead and label this first one here. Let's go yellow and blue again. And the first one's going to be our yellow one. All I got to do to put it in slope-intercept form is simply subtract the 1. And so we'll go ahead and do that. And I go to negative 1. I got a negative 1 slope, and so it'll look something like this. I can put a whole bunch of dots on this one. Okay, but I notice that this is a dashed. And again, those are things that we want to be careful of, is not to forget about dashed or solid. Then we test a point 0, 0. So I go back to the original. I plug in 0 for y, and I plug in 0 for x. And I get this statement, 1 is less than 0. Of course it's false. That's all we've been getting. So this is false. That's not always true. We always sometimes get true. And so there we go. We go ahead and shade below that line, because at the false region, we jump the fence. We always are looking for the true region. Let's go ahead and take a look at the second one here. On the second one, now notice that y is by itself. That's interesting. And if you remember, for Wiesen, when y is by itself, we're talking about a horizontal line. So this is simply a horizontal line at 1. If I convert it over to an equation, if I convert it over to an equation, you can see a y is by itself. It's going to be a solid horizontal. The inequality tells us it's going to be solid. So at 1, we got solid. And then what you'll notice is that all of our solutions are greater than 1, which means above. If you want to plug in 0 for y, you can see that, oh, 0, 0 is false again. So we would be shading above. Now, what we are looking for here is where do these two shaded regions overlap? And you can see here it's just a small, it's not really that small, it's actually infinitely huge, because the graph just looks small because the graph is just, the domain and range are just going to -6 and 6. But that's going to be our region of all of our solutions, is this triangular region right here, and that's what you want to shade in darker as your solution. So unlike systems of equations where you actually get an answer, here the graph is going to be the answer, and so the shaded region, we can't identify necessarily the shaded region algebraically, we just say it's bounded by those two inequalities. Let's take a look at a couple of weird ones here. We got some absolute values. Now, I know absolute values, what I want you to think is two cases, definitely two cases here. But take a look at both these absolute values, and these are the only ones you're going to be getting for in Algebra 2, is notice that y is by itself on both of them. So what you have are two horizontal lines. So we don't want to think v's. V's are when there are x's and y's involved. Okay, so we're not going to get that. So we're not going to get a V shape. We're actually just getting almost like three graphs. And so when we see these absolute values, I want you to think two cases. And this is going to be two horizontal or two vertical lines, depending on what's by itself. In this case, it's going to be horizontal for both of these since y is by itself. So let's label these. So number one, we actually have two cases. Case one, drop, okay, and solve. Case two, what we do is we drop, change the sign of the other side, correct? Okay, so what we have here is we have this absolute value inequality, which is y is less than or equal to 2, but we have two parts to it. We have y either is less than or equal to 2, or we have y is greater than or equal to negative 2. Now remember, we have to flip the inequality sign when I change the sign. So all these things that we did back in Unit 1 are coming back into play now. So hopefully you recall some of those things. So I have two cases here I've got to consider. And so I go, okay, let's go ahead and graph this first one, y equals negative 2. For both of these, it's going to be solid. And so I go, okay, negative 2, it's a solid line. And notice that for that one, it says that my solutions are greater than negative 2, which simply means it's above the line. The numbers that are above negative 2 are going to be up here. So I can go ahead and shade sort of above that line, would be fine. Okay, so it looks something like this. And then I do the second thing right here, same thing here, and I go, okay, well, I've got a horizontal at 2. You see where it's going to get a little messy. And then you have y is less than or equal to 2, so you'd shade this way. So what we want to do is we want to go ahead and let's just establish what we have currently. Where do these shaded regions overlap? Well, what you'll notice is it's sort of in the middle. Okay? Let's see if it makes sense to you. Do you remember this is called a compound inequality? That means it's either an and or an or. And if you read it, it's less than. And remember, ands are sandwiches. And so notice what we have are all the solutions are sandwiched in between these two boundaries. And so hopefully that makes sense to you. Because right now, that's where our solutions are. Now, we still have one more inequality left to graph. But so far, so good. Let's go ahead and graph the third one, actually, in this one, even though it's number 2. Okay? And this one's in slope-intercept form. So I'm going to go to negative 3, put a dot, have a positive 1 slope. And so I go ahead and I can graph this. This one's going to be dashed, and you can see right here it's dashed. Inequality is going to tell you that. So I connect the dots here, dash line, there we go. And I test 0, 0, which is in there. You can ignore the red and blue for right now. I'm going to plug in 0, 0 back into the original inequality, and I get 0 is greater than negative 3. Hey, there we go. We finally got a true statement. So we get a true statement. So 0, 0 is on the Fort Scott side. So we'll end up shading, and I'm going to put in green where we're shading here because it's pretty light so we can see. And so there we go. That's everything above that black line. Now, the objective, though, is we've got to figure out what area do all three. Where is it green, red, and blue? And so you can see, well, down here, that's not true, and up here, not true, and obviously down not here, and this is just red and blue. What you'll notice is sort of this trapezoidal shape right in here is where all three colors meet. And that's where there's that intersection. And so we would shade that in dark, and those would be where your solutions are at. So you can see a lot going on. You want to stay very organized the best you can as you go through these. Let's try another one here. Let's try this one down here. Again, it looks like two horizontal lines. So I go case 1, drop, and I'll solve. Case 2, drop, change the sign, flip the sign. Case 2, drop the sign, or excuse me, drop the absolute value sign, change the sign, flip the sign. A lot going on case 2. So I momentarily convert it to an equation just so I can get these graphed. This is going to be solid as well, so no dash there. Okay. And notice this one says, oh, it's everything above negative 1. So very similar to what we did up here. I go ahead and shade like this, everything above that one. So that one's going to be somewhat similar. Now we go ahead and I'm going to do case 1, which momentarily convert to an equation. So I go to 1. It's going to be solid. Okay, so it'll look like that. It says everything less than, so if I plugged in 0, 0, there's only a y to plug 0 into, but I get a true statement, so I get everything below. So let's just go ahead and pause here and figure out, okay, where are my solutions so far? My solutions so far are in between those two. That should make sense because, again, what kind of inequality are we talking about on this one? Being that it's a compound inequality, less than, it's an and, which is a sandwich, sandwiched in between those two boundaries. Okay? And then if we take a look at number 2, now notice this one, x is by itself. So you want to think x-ray, your vertebrae, so it's vertical, and you're going to be graphing a vertical line of 2. Now this one's going to be dashed. And so as we get going here, we'll have something like this at 2. And notice it says everything greater than 2. Which way is greater, right or left? Well, hopefully you've said right. Okay? And that's which way we're going to be shading. And then we're looking for where is it black and blue and red all over, okay? So it's one of those that, where is it black and blue and red all over? Well, it's going to be right here in between. That little rectangular region that goes forever. That's going to be our solutions right there, and we shade that in dark, and that would be our answers. We feel pretty good about that. Okay, so keep in mind those absolute values. We'll make V's. They're going to make either double horizontals or maybe double verticals. Watch your variables. Whichever ones are by themselves, we'll do that. So reference these if you get stuck on them. I think that will help. Taking a look at the last examples that we have, what you'll notice here on these is definitely, hopefully what you notice is, the slopes are the same. Now that's either going to tell you they're the same line or they're parallel. And there's a lot of different types of problems that we could encounter with these inequalities. And maybe we'll look at some of the weird ones in class. But for right now, let me just show you this one that obviously is labeled no solution. But let's make sure we understand why. So if I go ahead and graph this first one, I'm going to go ahead and graph this one. And I can't use white over here, so I'll use black. And so it's y equals 1/2 x plus 1. So notice the y-intercepts are different and the slopes are the same. So remember talking about that before. That obviously means that they're going to be parallel to each other. This one's going to be dashed. Again, that's going to be something you really want to pay attention to. If we do this, and then we got to test a point, 0, 0. So I plug in 0 for y, and I plug in 0 for x, and I get the statement 0 is greater than 1. I say false. Jump the fence, shade the true region. So I'm over here. Right? Hopefully you're staying with me. Rewind it if you need to. Looking at number 2, what we have is y equals 1/2 x minus 3. No same slope, but different y-intercept. So what we have here is a graph that looks very similar. It's also going to be dashed. This tells me right here it's going to be dashed. And then I test 0, 0, and what we get is 0 is less than -3. And we say, well, that's false as well. And so that's a false when I shade this side. I would shade opposite if it's false. So take a look, and if the question is, where do the two shaded regions overlap? Well, definitely not the middle, nothing there. This is just black and this is just red. They don't shade over each other anywhere. And so what we would put on something like this is we would say, oh, it's a no solution, and we put the null sign, something like that, to represent our answers for problems like that. So just because they're parallel, though, doesn't mean that it's going to be a no solution. And we'll look at some in class, but you can see where maybe instead of going down, what if I went up? You can see where there's going to be an overlap then. And so, you know, there's ways definitely to get answers even when the lines are parallel to each other. So don't assume too much. Make sure to go all the way through your process and get those graphed. Okay? Here's sort of a summary of some key elements of 3.3. Graphing inequality means that there should be shading involved, a lot of shading. And you're looking for where the shaded regions overlap. That's what you shade in darker. That's your solutions. And that's what we talked about with systems. When you have two or more equations, that's an indication or variables. That indicates that you need a system. If it's with inequalities, then you want to try to figure out what shaded regions, what parts do they share, because those are the solutions, and we're solving them simultaneously. So hopefully 3.3, you can reference what you've learned in the past, because if you can do that, this is a great, easy lesson for you. Making sure that you identify the difference between a system of equations, which is a point, or no solution, or an infinite number of points on a line, or a system of inequalities, which is where shaded regions overlap. Because when we graph inequalities, what comes to your mind? Hopefully shading does. Okay? All right, thank you.